to implement the deletion from the AVL tree. This is the video number 2. The first video was about insertion, but today we will implement the deletion. So we have this tree definition looking like this. This is our binary tree. It's represented as a polymorphic data type with two constructors for empty tree and therefore the node, which has some element of type A and left and right subtree which defined recursively. How we do the deletion from the AVL tree? Okay, at first we need to do the simple deletion from the binary search tree. Okay, and then we do this. We need to determine the first node in which can be possibly broken balance of the tree. And then going to up, we need to find the disbalanced node, do the rotation, and then continue to go up until there is no disbalance in our tree. Okay. So we need to start from simple deletion from the binary search tree. How we do the deletion in the binary search tree? Of course, at first we need to find the element which we want to delete. And from this point we have some cases. The first case is the deleted element has no child subtrees. It has no left subtree and right subtree. In this case, we can just remove this element because it is a leaf. We remove it from the tree, and that's all. Okay, and then at first point we talk about simple binary search tree, not a AVL tree. So if we find the element and it has no left and right subtree, then we just delete this leaf element. But what if this element has left and right subtrees? In this case, we need to choose some of these trees. For example, the left subtree. We need to find the minimum element in this left subtree and replace the deleted element by this minimum element. And there is also possible that minimum element itself has a right subtree. It has no left subtree because we always go to the left until we can't move left anymore to find the minimum. But it is possible that it has a right subtree. And in this case, we need to take this right subtree and attach it to the parent of our minimum element. So our minimal element go to the place of the deleted element, and the right subtree of the minimum element go to the parent of the minimum element. So this modification that we need to do in this case. But what if we have no left subtree on our deleted element? What if we have only right subtree? In this case, we need to find the maximum element of the right subtree, replace it, remove the deleted element and put the maximum element of this subtree to this element. And possible that maximum element have a left subtree, and they need to take this subtree, left subtree of the maximum element, and attach it to the parent of the maximum element. Okay. And according to this logic, we can say that they need four helper function. First function, I will call it delete minimum function, which take a tree and delete minimum element from it, and getmin function, which just take a tree and return the minimum element from this tree. and also delete max and get max function to get the maximum element and to delete the maximum element from the tree. So now I will implement these functions and show them. Okay, and here you can see that they have these 4 functions. For extracting the minimum element, this function take a binary tree of type A and produce to us a minimum element of type A. Also, we can delete this minimum element by this function. In this case, we take some tree on input and produce some new tree on output. Of course, we do the deletion recursively, we unpattern match the tree, and if we have the left subtree, we have the recursion here. So we construct our node again, but the length branch we take from the recursion function with the left subtree. And of course, since we have no left tree, this means that we found our minimum element. And in this case, we need to return the right subtree. Okay. To take the possibility to our recursion of to reconstruct the tree at all without the minimum element. And also in such a way getmax and deleteMax functions implemented. Now we need to implement the functions which do actually the deletion from our binary search tree. Okay, a moment and I will show you it. So here we have this function, which actually do the deletion. So how we do the deletion? If we delete a node, try to delete a node in the empty tree, we have this case, nothing have to delete, we must define this deletion as an empty tree. But if we have some tree with only one element E and empty subtrees, we must check that our deleted element is equal to E, and in this case the tree which has only one element transferred to empty tree, and otherwise it is returned as itself. So in this case we return the element which not present in our binary search tree. And if we have some tree which have the left and right branches, left and right subtrees, from here we have some cases. If our deleted element is greater than current element, then the recursion go deep to the right. Okay, and if our A is less than E, then with our recursion we go deep to the left. And last case, if our A is equal to A, if our right subtree empty, okay, I need to implement this empty function here. If our right subtree is empty, then must take the left subtree, extract the minimum from it, and put it to our deleted node E. So we have this node here, and we replace it with the minimum. And also we constructed the new left subtree, and right subtree stay the same. And how we define the left subtree? The left subtree is defined by the delmin function, which we already have here. So, and our minimum is defined as getmin function from the left subtree. And also in the case of the right subtree, we do exactly the same, but we modify the right subtree. this r underscore, it is defined as delete max from the right subtree, and a mix we get max and put it to the place of our deleted element e. Okay, and one thing I need to add here is the empty check function. How can we check that the tree empty or not? Of course, we can use an pattern matching here. If it constructed with the empty constructor, then we return true, and otherwise we define our function as false. Okay. Now, when we have this function which do the delation from our binary search tree, what we need next to implement the delation of the AVL tree? At first, we need to determine the node, the first node in which can possibly broken the balance. And how this node is defined? In which node we can break the balance after the deletion from the binary search tree. So I assume that we have already have the correct AVL tree, and we look at it as a binary search tree, and we do simple deletion from it as it is a binary search tree, without any care about the balance. But after they do the deletion from the AVL tree as a binary search tree, they need to determine the first node in which the balance can be broken. And actually this node will be in the case of then we have then the deleted element e have the left subtree, we extract the minimum. Okay, and in this case, then we extract the minimum of the deleted element e from the left subtree. In this case, the first possibly broken balanced element will be the predecessor of the minimum, I think. Sorry, successor of the minimum. Because the minimum possibly have the right subtree, and the root of this subtree, right subtree of minimum, will be a successor of this minimum. And in this point of this successor, the possibly balance can be broken, and we need to go up and check all the roots for a balance and do rebalancing. But if this minimum element has no right subtree, this means that the balance can be broken in the minimum element itself, and we need to take this start point to find the unbalanced element to the minimum. And also we have one symmetric case if the deleted element has no left subtree but has the right subtree. In this case, we take the maximum element from the right subtree, and this element possibly have the left subtree. And the root of this left subtree will be the predecessor of the maximum element. And this is root of this left subtree is the first node in which can be balance possibly broken. But if there is no left or right subtrees, in the deleted element, then they take as a first possibly balance broke element the minimum, the element itself, so element E. So according to this logic, I need to add two functions. The first function, get minimum successor, which retrieves the minimum element successor or minimum element itself if it has no successor, and get maximum predecessor, which extract the maximum element itself or the maximum element predecessor if it has the left subtree. Okay. Now look at these two functions. Definitions, they implement the logic about which I talk in just a moment later. So how we define the maximum element predecessor? If we have the tree with no left and right subtrees, then the maximum element has no predecessor and they return the element E itself. This is the maximum element. But if our tree has the no right subtree but has the left subtree, and this left subtree have some root P. In this case, they return this P because they can't move right to right anymore, and this is the maximum element. But if they have a right subtree, they move recursively to the right. Okay, and symmetric case for minimum successor by this function. Okay, now when I have these two functions, I can implement the function which takes binary tree, deleted element, and returns to me possibly the element in which the balance can be possibly broken, the lowest element, and from that element they need to go up to the tree and check the balance. Okay, let's look how can we implement such a function. So here is the implementation. This function, find the start disbalance point when we want to delete the element A from our tree. So you can see it on its type signature. It takes the deleted element, the binary tree, and possibly return the element with the broken, the first element with possibly broken balance. So if we have empty tree, of course, there is no element in which the balance can be broken. They return nothing. In the case if we have the tree with only one element, if our element is equal to A, then we can of course return the element where the balance can be broken. Otherwise they return nothing. But what if they have them, if they have tree with the left and right subtrees? In this case, if our element is greater than element of the node, we go to the right with recursion, and otherwise we go to the left until we find our deleted element. And then we check, like we do in the deletion, if the empty tree is if the right tree is empty tree, then we return the minimum successor of the minimum element from the left subtree, and otherwise we return the predecessor of the maximum element from the right subtree. And here you can see that I define these elements by these two functions. So the extracting the maximum predecessor or minimum successor. And this function which allow to us to determine the first disbalance node. They need it to start the traversing to the root and found the disbalanced nodes. Now, having all these functions, we can finally implement our delete from the AVL tree function. Exactly, this is the implementation of this function. And now I will explain how what it does. So, as I said, we start the deletion by simple deletion from the binary search tree. So we treat our AVL tree as a binary search tree and then do the deletion, which we already implement here by this function. Simple deletion from the binary search tree. And the define this new binary tree as unbalanced tree. So here I do this unbalanced tree name. What we do next? Then we find the disbalance, the disbalance node. So to find the disbalance, actually we use the find disbalance function, which was implemented in our first video about the AVL tree insertion. Actually, this function takes some node of the tree and go up to the root and finding the first node which is disbalanced. So it defined, you can see its definition. So actually this is its definition. So it's find the first node with balance greater than 1. So in balance, this is in balance node. And actually they do this by reversing the path from tree from the whole tree at all to the element A, and then they're reversing this path and moving from this element A to the root and checking the disbalance. So look at these two definitions to understand what actually happened. But now let's go again to our deletion function. So we need to find the disbalance start point SP disbalance node. Start point disbalance node here. We define it by our del dp function, which actually this is this function that finds start disbalance point on when we deleting the A, and we find this start point of disbalance node, and from this start point in the unbalanced tree we try to find this balanced node. Possibly they can find it, and so this expression can return nothing, but if it is found, they can apply the function go with partially applied unbalanced tree to the disbalanced node. And what this go actually do? So one thing I need to say that here we check our start point disbalance node. If we have no such node, there is no disbalance node after the deletion at all, then we return our unbalanced tree, I think, here. So if there is nothing to balance, then we return an unbalanced tree. But otherwise, if we have some disbalanced node, so we need to do the rotation in this node, and we do this with go function. And let's look at this function. So it takes some unbalanced tree, it takes some disbalanced node represented by this type, because every node is a binary tree of type A, and we return the balanced tree. Actually, this is our result, which we when extracted from just, and this is our final function definition in the case of is just starting point is balanced node. Okay, and now let's close a look to our go function. So if we go to go function, this means that we have the disbalanced node. So actually this is this node, we have a balanced tree after the binary search tree deletion, and we have this disbalanced node. What we need to do? We need to do the rotation. For rotation, I will talk about rotation later, but we have this function for rotation which take this balanced node and do the correct rotation which we need to do on deletion. So we construct the new rotated tree by replacing the disbalanced element with the new rotated tree in our unbalanced tree. So this thing will give to us the will restore the balance in our current disbalanced node. Okay, and then we need to find the new try to find the new disbalance from this balance element of the rotated tree. And if we find this new disbalanced node, then we can say that we have no there is no disbalance if why this is just, I think we need is nothing here. So so if I have no new disbalance node, then I go up to the tree from this disbalance point, then I can say that there is no disbalance, and there is no disbalance, so they can stop our go recursion, they return our rotated tree. But otherwise, if I found new disbalance, I need to repeat my rotation in this new disbalance node, which I can extract from this G from just, and as unbalanced tree we use our rotated tree. So we repeatedly iteratively repeat all these steps, going after the root until we find in any disbalanced node. Okay. And now finally we can look at our rotate function. So this function, to understand how it works, we need to understand the logic of the rotation when they do the deletion. Of course, to do the rotation, they need to determine at first our disbalance node, and we have it here on the input argument. So our logic which we do here provide to us that our rotate function receives as argument our disbalance node. And when they have this disbalance node, we need to look at the left and right subtrees of these disbalance nodes. So here them are, left and right, and our disbalance element. So and we need to check 4 cases. Actually we need to check 2, and other 2 is symmetric. The first case, then the left subtree of our disbalance node is greater or equal than the right subtree. In this case, they do the rotation, left-left rotation. So I assume that you know a little bit about how to rotate the trees, then they delete in the node. I assume that you know theory about this. And here I only do the implementation. So if we have the left subtree or the disbalance node is greater than right tree, then they do LL rotation. If the right tree is greater than left tree, then they do the LR rotation. So here I also need to say that the one moment. Here we are not checking the left and right subtrees of the disbalance element. So at first they need to determine the left or right tree of the disbalance element. There they actually do the insertion. And if they do the insertion to the right subtree from this disbalance element, then they go to the left. And we look to this left subtree and extract the this subtree, left subtree and the left right subtree, and looking at them. But if they do the insertion to the left, then they go to the right. They go to the right and look at this right subtree, and here then pattern match it and look at the right subtree, left subtree, and right subtree, right subtree. Okay, and here we have 4 cases when we go to the left, opposite the insertion side, and left greater or equal than right. Actually, this is this case. So how we define the insertion? How we define the insertion? Was the tree inserted to the left or to the right? In the previous video we defined some function. Let's look at it. It's called find path. Find path. You can see here this function. It's take some element, some binary tree, and produce a path to this element in terms we go left to a right or right. There's the list of this direction. So every path from a root to element can be encoded via via list of these directions. And here I want to rewrite a little this function. I will remove the 2 from here, from the name, and I will provide this as argument. So let's take this counter, and I place this counter to this helper go, which actually do the traversing down to the tree this count number of times, and every time they decrease this counter and collect the left or right direction to the list. So in the previous video we need this function here to find to detect the rotation left right, but here I will modify it, because here I need this function. I need to know only one direction from the disbalanced node to node in which possibly can be balance broken. Start point disbalanced node, okay, which we defined by this function. Where is it? By this function, okay. So here they take our disbalance node, and it is a tree. It's represented as a tree, and they move to our first possibly broken balance node with only one step, and this gives to us the direction. Move it to the left or move it to the right, and of course we move into the subtree where they insert. No, wait, sorry, delete the node, because the balance actually broken in that point that they do the deletion. So and here this function return to us this left or right, and we can check it. If we insert into left, of course this thing gives to us the left direction, and the insert into right, this thing gives to us the right direction. And here we can see that if we insert into the right, we go to the left, we go to the opposite, and we check in the left and left right heights. So we have these 4 cases, and these cases determine the rotations. And we already have the rotations in our previous video. In the when they do the insertion, they have these functions, and actually I can extract them from here, because they take only one argument, this balance node, and do the rotation. So if I extract these things from here and put them here, I will have these functions which I can now use in other functions, not only in the insert, but you can see these functions needed in delete also. And now I think we can try to compile this thing. So let's try to load this file, and you can see it is loaded. And now I need to provide some examples to see that our implementation is working as expect from the deletion of AVL tree. So at first, of course, I need to construct the tree. I have this function from list, which take the list of some elements, some numbers, which will represent me the AVL tree. Actually, this is the insertions to our AVL tree, which correctly do the rebalancing. And let's check this. So you can see we have this balanced AVL tree. I think there is no balance broken here. And now I can try to delete from this tree something. For example, what if I remove 2 from here? Okay. What if I remove 2 from this tree? And you can see actually the 2 is removed and we have the new balanced, correct balanced binary search tree, actually AVL tree. Okay, now let's try to remove, for example, from this tree, let's remove 5. And you can see that if we remove the 5 from here, we have a new root 2. And a new balanced subtrees. You can see that all the balanced is correct here. And I hope that I don't do any errors. I don't want to do testing. If you find any errors in this logic, please write comments. So actually this is our final implementation of deletion. I try to do it much closer to the definition, actual mathematical definition of the deletion from the AVL tree without any optimizations. And I think this is expressive solution. And I hope there is no errors here. So guys, I think that's all for today. Thanks for watching. Push like button, push subscribe button, and write comments. See you in the next videos. Bye bye.